Hello everyone. Welcome to the practical on transmission line compensation in the Power Systems 1 module of semester 4.
The objectives of this practical are to investigate number 1, the effects of series capacitors on the limits of power transfer over a transmission line, and number 2, the effects of shunt capacitors on a transmission line, where the terminal voltages are fixed in both the cases. Now, let's first understand the theory parts. So, why do we need reactive power compensation? Okay, let me explain it this way. When electrical energy is used as AC, reactive power needs to be supplied along with the active power. Active power contributes to the energy consumed or transmitted, while reactive power does not contribute to the energy. Reactive power is either generated or consumed by every component of the system: generation, transmission, and distribution. Most of the loads are inductive and must be supplied with lagging reactive power. Therefore, reactive power must be supplied and reactive power compensation is needed. So, reactive power compensation in power systems can be either shunt or series. The most common form of reactive power compensation is by connecting shunt capacitors to the line. Now, let's see the reasons for using shunt capacitances. Shunt capacitances are used for voltage regulation, that is, to maintain the voltage within the required levels. Load of the transmission line changes over the day. As a result, the voltage at the substation bus and the load bus varies. Additionally, the load power factor is always lagging. This is because the loads are usually inductive. Therefore, a shunt-connected capacitor bank at the substation can raise the voltage when the load connected is high. Another reason is to reduce the power loss. A shunt capacitor bank improves the power factor. Therefore, it reduces the current flow. This will result in a reduction of I2R losses. Thirdly, increased equipment utilization. Using shunt compensation with capacitor banks reduces the kVA loading of lines, transformers, and generators. Therefore, more power can be delivered without overloading the equipment. That's all about the theory parts for this practical. Now, let's move on to the practical.
First, let's have a look at our setup. I'm sure you all know what this is. Yes, it's a variac. This can give an alternating voltage supply of 0 to 270 volts. So now you can have a quick look at the other equipment which we are going to use for this practical. Right, this is the rheostat to change the load. And this is the rheostat which we are going to use as a fixed 6 ohm resistor. Yes, this is our capacitor bank. So these are our ammeters and voltmeters to measure the currents and voltages. This is a single phase wattmeter. And this is an inductor with a maximum inductance of 0.15 henries. So this is how we have laid out the equipment to start off with part 1 of the practical series capacitance test. And this is the circuit that we are going to connect for this part. After connecting this simple circuit, first switch on the supply. And then adjust the variac output to be 100 volts. This is our sending end voltage. So, as you can see here, the sending end voltage is now 100 volts. Okay, after that, let's make our receiving end voltage to be 90 volts. So how can we do this? Simply change the load resistance until the receiving end voltage is 90 volts. Make sure to keep the sending end voltage at 100 volts and the receiving end voltage at 90 volts throughout this test. Okay, now let's short circuit the capacitors. That means we are not going to connect the capacitors here. Also, make sure to keep the receiving end voltage at 90 volts. Let's take the ammeter reading. As you can see here, it's 0.5 amperes. And now let's take the wattmeter reading too. So this is the 5 ampere range and this is the 240 volts range. The wattmeter. So since we have used 5 amperes as the current range and 240 volts as the voltage range, our multiplication factor is 10. So the wattmeter reading is 4 into 10, which is 40 watts. Now let's connect the maximum series capacitance and increase the load until the original voltage conditions are met. Then take the current and power readings. And we have to repeat this process for different values of capacitances. These are the readings that we have obtained for the two cases with the capacitor bank short-circuited and with the capacitor bank connected in series. Please add this to your observation sheet. So these are the calculations that you need to do under the series capacitance test. Now let's move on to part 2 of the practical shunt capacitance test. This is the circuit that we are going to connect for part 2. So now you can see how we have connected the circuit as shown in the previous figure. Here the capacitor bank is connected in parallel to the circuit. Since this is a simple circuit, we are not going to see the connections one by one. Okay, so let's get started with the practical. Here also, adjust the variac output to be 100 volts. This is our sending end voltage, which is 100 volts. Now, let's make our receiving end voltage to be 90 volts by changing the load resistance as previously. Here, we have connected a capacitance of 35 microfarads in parallel. Now, let's take the ammeter and wattmeter readings. As you can see here, the reading of ammeter A is 1.15 amperes. The reading of ammeter A1 is 1.5 amperes. And finally, the wattmeter reading is 100 watts. So these are the readings that we have obtained for different values of shunt capacitances. Please add this to your observation sheet. This is the calculation part that you need to do on the shunt capacitance test. These are the questions to be answered under discussion in your coursework. hope you enjoyed this practical on the use of series and shunt capacitance in transmission lines. Thank you.